In the quiet immensity of the inner solar system, where light from the sun stretches into immeasurable distances and the void folds into a soft, unbroken hush, a stranger drifts. It is small, a fragment of darkness, hardly more than a ghost against the brilliance of the solar wind, yet it carries with it the weight of an entire unknown history. Long before it crossed the heliospheric boundary, long before it brushed against the gravitational pull of the sun, it wandered alone through interstellar night for tens of millions of years. Now, for the briefest blink of cosmic time, it has come close enough for humanity to witness its awakening. The object named 3I Atlas moves with a stillness that belies the turmoil within it. To astronomers, it is more than a comet, more than a fragment of ancient rock, more than a visitor that slipped between the stars. It is a question, wrapped in ice and dust, drifting through a realm governed by physics that fail to fully contain it. It has begun to glow, to breathe, to shed materials as though emerging from a cold, eternal sleep. And something in its behavior whispers of a complexity that makes even seasoned researchers fall silent. For weeks, NASA has watched quietly. Telescopes have followed its faint arc across the sky. Instruments have captured readings that defy easy interpretation, and analysts have sifted through data points that behave less like the predictable signals of a comet and more like the shifting language of an unknown system. The agency's public voice, usually steady and forthcoming, has remained cautious, not withholding, merely patient. There is a difference. Silence, in the realm of science, is rarely secrecy. It is often reverence. Now, that silence has broken, and the timing is no accident. Even as NASA prepares to release its awaited high-resolution imagery, images that many believe will redefine how interstellar visitors are classified, another force is racing outward from the Sunday, a pulse of solar fury, a billowing eruption of plasma and magnetic fields, a coronal mass ejection born from the violent twist of magnetic loops on the solar surface, has torn free and hurled itself across the solar system. It expands like a burning tide in all directions, dragging shockwaves of charged particles with it. Most CMEs pass unnoticed by human eyes. They sweep harmlessly through the emptiness between planets, or dissipate long before reaching anything substantial. But this one travels along a rare and narrow geometry, a corridor of space where its trajectory intersects precisely with the path of 3I Atlas. Two wanderers, one ancient and cold, one newborn and incandescent, now drift toward an encounter written not by intention, but by cosmic coincidence. This approaching meeting carries weight. For the first time in human history, a solar eruption will strike an interstellar object, while a full suite of scientific instruments watches closely. The sun, in its restless violence, is about to touch something that does not belong to this system. An emissary from elsewhere will feel the breath of a foreign star, and humanity will witness the reaction. Will the impact shred the tail that has only recently begun to form? Will it distort the magnetic sheath that surrounds the visitor like a fragile cocoon? Will it reveal the true structure of the nucleus, whether it is solid rock, porous ice, or something stranger, something shaped by conditions not found near our sun? The uncertainty is what gives the moment its gravity. Astronomers know well how comets respond to solar storms, yet they also know that 3I Atlas has already defied expectations. Its coma behaves as though governed by electromagnetic patterns more intricate than typical solar system visitors. Its jets form rigid structures where physics predicts diffusion. Its rotation is slow and tumbling, yet the materials around it behave as though held in ordered channels. These contradictions are not dramatic enough to rewrite physics, but they are strange enough to demand attention. The CME approaches. The object glows. NASA prepares to unveil the images it has held back, waiting until the data could be vetted and confirmed. And around the world, astronomers, professional and amateur alike, watch the sky with a shared sense of anticipation. Not fear, not dread, something quieter, something older. Humanity has always turned to the heavens with the same mixture of awe and longing. The stars do not answer, yet they offer glimpses, hints, brief encounters that reveal just enough to deepen the mystery. 3. Atlas is one such encounter. It does not threaten Earth. It does not bend its path in unnatural ways. It simply drifts, bearing secrets of a place humanity has never seen, carrying the quiet memory of a different sun, or perhaps no sun at all. And now, the star that governs our own system reaches out to meet it. In this meeting between a solar storm and a visitor from the deep, ancient night, something profound unfolds. Not a battle, not a crisis, but a moment of cosmic intimacy, a reminder that even in the silent vacuum of space, interactions are ceaseless, connections are everywhere, and the universe remains a place of constant, unfolding story. The stage is set. The traveler approaches the breath of the Sunday. NASA prepares to show the world what it has seen, and somewhere in the vastness between Earth and star, 3i Atlas continues onward, indifferent to the attention, carrying its mystery into the heart of a solar tempest. Long before the world spoke its name, and long before NASA's cautious silence drew attention, 3i Atlas appeared only as a faint irregularity in the sky, an object so dim, so unassuming, that it might easily have been dismissed as noise in a telescope's field of view. Its discovery was not dramatic, no sudden alarm, no shimmering streak across the heavens. Instead, it began with the quiet, methodical work of astronomers engaged in a routine survey of the skies. The Asteroid Terrestrial Impact Last Alert System, known simply as ATLAS, is a network designed to watch for dangerous objects. Its purpose is to scan for fast-moving bodies that could threaten Earth. Its wide-field telescopes sweep the night sky in repeated passes, searching for transient sources of light that shift between one exposure and the next. In such an environment, thousands of candidates appear each night: satellites, glints, noise, cosmic rays striking a detector, and ordinary asteroids crossing the ecliptic. On one of these nights, the faint speck that would later be called 3i Atlas drifted across an exposure. It did not glow with the typical brightness of a near-Earth asteroid. It did not carry the delicate fan of a nearby comet. It simply moved too quickly, too strangely, and along a path that did not bend the way objects bound to the sun's gravity usually bend. At first it was catalogued, logged, and compared to known databases. Nothing matched. For several days, the tiny traveler was observed again and again. Each new data point traced out a motion that felt wrong, or at least unfamiliar. When astronomers plotted its arc backward through space, they found no elliptical orbit that could contain it, no gentle parabola of a returning long-period comet, no backward projection that would place it anywhere near the Oort cloud. Instead, the projected path stretched outward beyond the heliosphere, beyond the gravitational influence of the planets, all the way into interstellar darkness. Its origin was not a distant corner of the solar system. It was elsewhere. That recognition carried an echo, a memory from only a few years earlier. Humanity had seen an interstellar traveler before 1i, Oumuamua, the first confirmed object from another star system. It had tumbled past Earth in 2017 with a speed and trajectory that left scientists scrambling to revise their expectations. Then, in 2019, another 2i, Borisov, swept through the solar system with a shimmering, comet-like form. Each arrival had been a revelation, a reminder that stars cast debris into the galaxy like seeds, and that our own solar system is not separated from the wider cosmic neighborhood, but immersed in it. Yet 3I Atlas, from the moment of its discovery, carried a different signature. Its coma was diffuse, strangely shaped, extending farther than expected for an object still so distant from the Sunday. Its brightness fluctuated in ways that suggested unstable or complex outgassing, and though the faint details were difficult to resolve, its motion felt neither comet-like nor asteroid-like, as though it belonged to a category still unnamed. This ambiguity is what drew researchers to it, and as more telescopes turned toward the faint traveler, questions began to multiply. What was the composition of this object? From what kind of system had it been expelled? How old was it? What natural event, gravitational scattering, planetary migration, or stellar disruption, had flung it into the interstellar deep? Even before NASA's later involvement, observatories across the world tracked 3I Atlas with a mixture of caution and awe. Infrared surveys attempted to capture its thermal profile. Optical telescopes studied its coma, looking for signatures of common volatiles: water, carbon monoxide, carbon dioxide. Some of these chemicals appeared faintly, others were absent or drowned in broader signals that resisted easy interpretation. It became clear that this visitor was not simply another icy relic like the comets that populate the outer reaches of the solar system. Some scientists proposed that it might be the shattered fragment of a planetesimal, something formed around a distant star long since faded. Others suggested that its composition might be altered by cosmic radiation, sculpted during millions of years, exposed to interstellar space. Still others speculated that the object might contain more exotic materials, formed under conditions not present in the early solar system. As weeks passed, the data accumulated, and though the object remained faint, each measurement nudged the narrative further from certainty. It rotated slowly, almost lazily, around an axis that itself appeared unstable. It shed gas in intermittent bursts, as though waking in pulses rather than in a smooth, predictable bloom of activity. Its trajectory carried no hint of threat to Earth, but its behavior carried the unmistakable signature of something foreign. It was around this time that NASA's deeper participation began. High-powered instruments, including the Hubble Space Telescope, trained their gaze upon the interstellar visitor. The images that emerged were sparse, yet illuminating. The nucleus, the solid heart of the object, appeared small, perhaps only a few kilometers across. But the coma surrounding it stretched to hundreds of thousands of kilometers, an expanse so enormous that it rivaled some of the largest comae ever recorded. This scale was unusual. It suggested either powerful outgassing or some form of material that reacted strongly to the sun's early warming. Whatever lay within 3I Atlas was awakening dramatically. But it was the shape of the coma that stirred the most discussion. It seemed inconsistent, shimmering with hints of jets that blinked in and out of visibility depending on the viewing angle. And behind this complexity was a truth that scientists hesitate to state prematurely. The object behaved unlike any comet yet studied. As NASA gathered more data, and as the object approached the inner solar system, the agency made a deliberate choice to wait before speaking. New objects bring excitement, but they also bring ambiguity. Scientists know the danger of early conclusions. Data must be refined, verified, calibrated, especially when dealing with something that comes from between the stars. Meanwhile, Atlas continued its nightly sweep. More observatories joined the effort, and a quiet realization spread among astronomers. This was not simply the third interstellar object. It was a new kind of visitor. Its awakening, its coma, its jets, its magnetic interactions, all of it hinted that the story of 3I Atlas would be more than a brief scientific footnote. It would become a chapter in humanity's ongoing conversation with the cosmos, one written not in words, but in light, dust, plasma, and the slow unfolding of a mystery no one yet fully understood. And all of this unfolded before the sun's fury reached out toward it, before the CME began its relentless journey, and before NASA broke its silence. When an interstellar object drifts into the inner solar system, the world takes notice. But when NASA falls quiet in the face of such an arrival, attention sharpens into a different kind of anticipation, a waiting that feels deliberate, almost ceremonial. For weeks following the initial identification of 3I Atlas, the agency spoke only in fragments. Small confirmations, brief acknowledgements, no firm declarations. In a scientific era shaped by rapid communication and public briefings, the silence was conspicuous. Yet this was not the silence of secrecy. It was the silence of discipline. NASA has learned, over decades of discovery, that the universe often defies the clarity of first impressions. Early data can mislead, initial imagery can distort. Objects from beyond the solar system carry behaviors that challenge assumptions rooted in local celestial mechanics. And so, instead of offering premature analyses or hasty interpretations, the agency chose patience. Observations streamed in quietly through the Deep Space Network, through ground-based observatories, through Hubble itself. But nothing was announced until every pixel and signature had been calibrated against the noise of deep space observation. Behind the scenes, teams across several NASA centers worked with an intensity that belied the agency's outward calm. Astrophysicists at Goddard examined the early reflectance spectra. Planetary scientists at JPL ran orbital simulations to ensure that nothing in its trajectory posed a risk to Earth or any spacecraft. Photometric analysts corrected the faint halo of its blooming coma, trying to extract the size and shape of the nucleus hidden within. All of this unfolded under the weight of a complication. 3I Atlas did not behave like a conventional comet. Its coma expanded in unexpected directions. Its jets activated in fits and pulses rather than in steady arcs. The surrounding dust cloud swelled and contracted as though responding not just to sunlight, but to a shifting internal mechanism that no model fully captured. Each new dataset answered one question and raised three more. Had NASA spoken too early, the agency risked setting expectations or drawing conclusions that the data had not yet earned, and so they waited longer than many expected. Meanwhile, outside NASA, speculation thrived in the vacuum. Independent astronomers released their own images and measurements, with interpretations ranging from cautious to sensational. Some noted the unusually large coma, comparing it to the massive outbursts seen in hyperactive comets. Others observed the structured jets and wondered whether electromagnetic shaping was at play. A few, less tethered to scientific conservatism, proposed far stranger theories. The public conversation swelled, dynamic and often chaotic, fueled by the mystery of a traveler from the interstellar dark. Scientists inside NASA watched this discourse unfold with a familiar mix of understanding and restraint. They knew that interstellar objects ignite the human imagination like few other cosmic phenomena. They also knew that premature commentary from an official source could shape the narrative in ways difficult to correct later. Hyperbole might overshadow reality. Skepticism might overshadow significance. Silence, though difficult, protected the integrity of the unfolding data. What the public did not see, at least not immediately, was the imagery gathered by instruments positioned far from Earth. Hubble was one source, but not the only one. Assets in orbit around Mars had a uniquely favorable vantage point, and one of these, the high-resolution imaging science experiment known as HiRISE, captured imagery of 3I Atlas from a distance that allowed angles impossible from Earth's surface. Though taken on October 3, the data required painstaking reduction to strip away noise, correct for the spacecraft's motion, and account for the deep glare of sunlight scattered through its coma. NASA's analysts knew what such images might reveal: the shape of the nucleus, the orientation of the jets, the symmetry or asymmetry of the coma. But they also knew that misinterpreting such complexity would be far worse than waiting for certainty. It was essential to eliminate every artifact of processing before releasing the data. Another reason for the delay lay in an unexpected coincidence of timing. As early observations accumulated, the sun's activity surged. A volatile region on the solar surface produced repeated eruptions of plasma and magnetic fields. Solar physicists monitored these events with increasing interest, noting that the geometry of one particular eruption, a coronal mass ejection, set it on a trajectory that would pass near, or perhaps directly across, the path of 3I Atlas. This presented a rare scientific opportunity. For decades, solar physicists had studied the effects of CMEs on comets within the solar system. These interactions could cause tail disconnection events, magnetic piling, sudden shifts in ion emission, and dramatic distortion of the coma. But never in recorded history had an interstellar object been positioned to receive such a solar impact while under detailed observation. NASA's teams sensed the magnitude of what was unfolding, a moment where the sun's raw energy would collide with matter formed under a different star. A meeting between environments shaped by different origins, different histories, different cosmic conditions, a natural experiment of extraordinary value. The agency chose to gather every possible frame of data before releasing conclusions. This cautious approach was not new. NASA had behaved similarly after the arrival of Oumuamua, waiting until models stabilized before issuing press statements. With 3I Atlas, however, the stakes were more complex. Its behavior diverged far more noticeably from established comet physics. The agency needed to ensure that any information released would not mislead, confuse, or provoke unnecessary alarm, particularly given the public fascination surrounding interstellar objects. When the silence finally broke, it did so with a clarity that felt prepared, deliberate. NASA announced both the upcoming release of high-resolution images and the live stream that would accompany them. The timing was precise. Analysts had verified the nucleus estimates from Hubble. Jet structures had been cross-referenced against observations from ground-based telescopes. The behavior of the coma had been evaluated against the solar wind environment. Enough data had stabilized to allow responsible public explanation. And beneath this official announcement lay an unspoken acknowledgement. The story of 3I Atlas was not finished. It was only beginning. Because even as NASA prepared the release, the CME was still crossing the solar system. Its magnetic fields twisted, its shock front expanded, and its charged particles streamed outward with relentless velocity. Approaching 3I Atlas at tens of millions of kilometers per hour, the solar storm promised a moment of profound scientific revelation. Would it tear the forming tail apart? Would it compress the magnetic sheath surrounding the coma? Would it trigger a burst of outgassing so intense that the object brightened visibly overnight? The agency's silence had not been a void, it had been preparation, a gathering of threads, a cautious weaving of evidence before the cosmic event arrived. When the images and data would finally be unveiled, they would do more than satisfy curiosity. They would form the foundation of an unprecedented experiment, the sun reaching out to an interstellar visitor, and astronomers watching to see how matter from distant space responds to the breath of a new star. Silence had given way to the first words of a story still unfolding, still deepening, still spiraling into questions that stretched far beyond anything the solar system alone could explain. The deeper astronomers looked into the behavior of 3 ATLAs, the clearer it became that something about this visitor did not align with the quiet rules governing ordinary comets. From the earliest images, even before NASA's silence lifted, anomalies threaded through its motion and structure, subtle at first, then unmistakable. What began as curiosity shifted into scientific unease, the kind that emerges when an object refuses to fit within familiar frameworks. The first strangeness lay in its trajectory. Interstellar objects, freed from the gravitational tether of any single star, follow hyperbolic paths, long, open arcs shaped by the sun's passing influence. Both Oumuamua and Borisov had followed such courses, slipping around the sun and departing again into the dark at speeds that defied capture. 3I Atlas was no different in that fundamental pattern. Yet, the details of its motion deviated from expectations. Its orbital data showed faint, non-gravitational accelerations, subtle, persistent deviations from the track gravity alone would dictate. These deviations were not unprecedented. Comets experience similar forces when jets of gas erupt from their surfaces. But in this case, the accelerations appeared inconsistent, shifting as though driven by something more complex than standard outgassing. Worse still, when analysts attempted to match these deviations to the visible jets within its coma, the behavior did not fully align. Jets appeared in orientations that did not correspond neatly to changes in the object's motion. They pulsed irregularly, sometimes brightening for hours, sometimes fading to near invisibility, without the predictable consistency seen in solar system comets. It was as though the internal mechanisms of 3I Atlas, its cracks, vents, and reservoirs of volatile material, were arranged in patterns unfamiliar to typical cometary physics. But if its motion raised eyebrows, its coma raised questions far deeper. Even at distances where ordinary comets remain dormant, 3I Atlas bloomed. A diffuse cloud of dust and gas enveloped it, expanding into a structure so vast that early estimates suggested a diameter approaching half that of the Sunday. Such a size was extraordinary. Comae do grow dramatically as comets near the Sun, but rarely with such intensity at such distances. Something within the interstellar visitor was awakening early, shedding layers that had perhaps been locked in darkness for millions of years. And yet the coma did not expand evenly. Patterns of density curled through it like invisible fingerprints. Some arcs glowed with higher reflectance, hinting at concentrations of dust that clumped where models predicted smooth dispersion. Others faded abruptly, as though sculpted by forces stronger than sunlight alone. This asymmetry led to the next anomaly, the jets. Typical cometary jets arc outward as sunlight strikes volatile materials, sublimating them into gas that escapes through cracks in the nucleus. These jets broaden with distance, diffusing into the surrounding coma. But around 3I Atlas, several jets maintained a surprising coherence. Thin lines of gas and dust extended through the coma with structural clarity less like wisps of vapor, more like filaments shaped along invisible channels. For an object rotating slowly and tumbling unpredictably, such stability was perplexing. Dust plasma physicists, trained in the behavior of charged particles interacting with the solar wind, offered one possible explanation. As the object approached the Sun, its dust became increasingly ionized. Charged grains could then be guided along magnetic gradients formed within the coma itself, creating channels where particles flowed in structured paths. Such dynamics, while plausible, remained speculative. No comet within the solar system had displayed such distinct and persistent channels. Compounding this complexity was the brightness variability of the jets. They brightened not only when the sun's rays grew stronger, but also in patterns that seemed to correlate with solar wind conditions. Observers noted that during periods of heightened solar activity, 3I Atlas's coma behaved almost reactively. expanding or condensing in ways that suggested sensitivity to magnetic fluctuations. If true, this implied a level of electromagnetic interaction rarely observed with such intensity in cometary bodies. Then came the anomaly that troubled scientists the most: the anti-tail. An anti-tail, also known as a sunward-facing tail, is not unheard of. Under certain geometries, dust particles can move in such a way that they appear to form a tail pointing toward the sunday, but in the case of 3I Atlas, the anti-tail displayed a sharpness, a persistence, and a directionality that defied the expectations of many researchers. Anti-tails typically arise from specific orbital alignments that produce distinct optical effects. This one retained structure even when geometries shifted far more than models would predict. Moreover, the anti-tail did not act independently. It was braided with other jets, forming a tangled but strangely ordered structure around the nucleus. Some scientists likened it to a skeletal framework of dust, shaped by electromagnetic interactions akin to those seen in complex dusty plasma experiments on Earth. Still, anomalies alone do not make a mystery. They make an invitation to deeper study, and the deeper astronomers probed, the more the object resisted categorization. It rotated slowly, completing a full cycle in roughly 16 hours. Such a leisurely spin should have allowed the jets to smear into broad, indistinct arcs. Instead, their stability hinted at internal or environmental constraints, keeping them aligned. Perhaps cavities within the nucleus vented gases preferentially in certain directions. Perhaps layers of the object possessed differing compositions, leading to unexpected interactions with the sun's heat. Or perhaps interstellar exposure had altered its surface chemistry in ways that made it behave differently from comets formed within the solar system. Even the nucleus's size, a fundamental parameter, remained uncertain. Hubble's estimates suggested a diameter of up to 2.8 kilometers, but other analyses, relying on photometric modeling, hinted at possibilities far larger, perhaps tens of kilometers. Without a clear measurement, every calculation depended on assumptions, and assumptions, in the realm of interstellar bodies, are fragile. This uncertainty only deepened the scientific tension. Some researchers proposed that 3I Atlas might be the shattered remnant of a protoplanet ejected from a chaotic young star system. Others suggested it could be a fragment of a disrupted moon or planetesimal, shaped by tidal forces during a distant gravitational cataclysm. Still, others wondered whether its unusual coma dynamics were the legacy of cosmic ray sculpting during its long exile between the stars. But whatever its origin, its current behavior defied the expectations of comet physics. The solar wind seemed to interact with it strongly. The coma's structure responded to changing magnetic fields with unusual sensitivity. Jets behaved as though guided, not merely released. And as the sun's activity increased, patterns emerged that hinted at complexities still hidden. By the time NASA prepared to reveal its high-resolution imagery, the scientific community understood something essential. They were not simply observing a comet. They were observing an object whose physical and electromagnetic behavior belonged to a category still unnamed. This was the heart of the scientific shock. Not that 3I Atlas was interstellar, but that interstellar objects might follow rules unfamiliar to local celestial mechanics. That the universe beyond the heliosphere might shape bodies differently. That the physics governing dust, gas, and ice among distant stars might produce structures that challenge the assumptions built on studying comets born under our sunday. 3I Atlas was not threatening. It was not anomalous in a way that endangered Earth, but it was strange in a beautiful, revelatory way, reminding scientists that even after centuries of exploration, the cosmos retains the power to surprise. The discovery phase had ended, the shock had begun, and the mystery around 3I Atlas was deepening with every new beam of sunlight it encountered. The Sun is not a quiet star. Even in its calmer cycles, its surface ripples with slow, boiling granules of plasma, each one larger than entire continents on Earth. But in moments of heightened activity, when magnetic fields twist into knots, when energy rises through the solar atmosphere and erupts outward, the star's serenity fractures, filaments snap, loops brighten, shock waves ripple along the corona. And deep within this radiant turbulence, something ancient and formidable is born, a coronal mass ejection. The CME that now travels toward 3I Atlas began as a flare-like disturbance along a restless region of the Sun, an active sunspot cluster that had, in the weeks prior, delivered storms powerful enough to rattle Earth's magnetosphere. Though this sunspot group had rotated out of direct view, its magnetic vaults remained poised at the solar limb, just beyond the horizon from Earth's perspective. There, in that half-hidden region, the magnetic fields twisted fiercely enough to trigger an eruption. For a moment, the very edge of the solar disk shimmered. A surge of ultraviolet radiation lit the corona in sharp, veined arcs. And then the eruption unfurled, a blossom of plasma, a billion tons of charged particles swept upward and outward, escaping the Sun's gravity with the momentum of a planetary explosion. Expanding, cooling, and accelerating, the CME grew into a vast shell of magnetized particles, stretching across millions of kilometers as it pushed into interplanetary space. Most CMEs disperse harmlessly, fanning out into directions where only empty vacuum awaits them, but this one launched along a trajectory that aligned by cosmic coincidence with the orbital path of the interstellar visitor. A direct shot, as some solar physicists murmured under their breath. Not toward Earth, not toward Mars, but toward 3I Atlas, which drifted slightly above the ecliptic plane. The alignment was uncanny. From simulations run by space weather models, the CME fanned outward in a broad but coherent cone. As researchers plotted the object's position within this expanding wave, the geometry became undeniable. The ejection was not merely passing near 3I Atlas, it was heading straight toward it. The impact, projected for the 22nd of November, would unfold with the force of a sustained electromagnetic storm, a meeting of solar power and interstellar matter unlike anything previously observed. News of this geometry spread quietly at first, whispered among heliophysicists and comet researchers who recognized the significance immediately. For decades, scientists had studied the ways in which CMEs influenced comets born of the solar system. They had seen tails sever cleanly by magnetic compression, as though sliced by invisible blades. They had recorded sudden shifts in ion emissions, bow shocks forming around nuclei, and structural distortions in dust environments. But such events, while fascinating, belonged to objects shaped by our Sun's rhythms, objects that understood, in a sense, what it meant to orbit a temperamental star. 3I Atlas was different. It had never encountered a CME from this Sunday. It was born under a different gravitational cradle, hardened in different cosmic winds, sculpted by electromagnetic conditions utterly unlike the heliosphere's environment. Its surface chemistry, dormancy cycles, and dust composition were formed under alien conditions. And now, as it bloomed into activity while approaching perihelion, it was poised to face a solar storm that would test not only its structure, but the foundational physics governing interstellar bodies. Scientists imagined what might unfold. Would the CME tear apart the object's fragile antitail, revealing the inner structure of its ionized dust environment? Would the magnetic field surrounding the coma collapse or flare, compressing into shapes that gave away its composition? Would the nucleus brighten or dim, or perhaps fracture, unleashing a sudden burst of activity? Or would the object's unique electromagnetic environment resist the storm in some unexpected way, behaving differently from any comet yet studied? Such questions did not emerge from fantasy, but from precedent. The Rosetta mission, tracking Comet 67P Churyumov-Gerasimenko, had recorded the dramatic effects of a CME impact firsthand. When a solar eruption struck that comet, the magnetic field around the nucleus surged from 50 nanotesla to nearly 300 nanotesla, an increase so sudden that instruments were briefly overwhelmed. Dust behaved erratically, plasma boundaries collapsed and reformed. The comet's environment became, for hours, a chaos of charged particles and electromagnetic interactions. Scientists now imagined an event of similar magnitude unfolding around 3I Atlas, but with one critical difference. The interstellar visitor's coma was unimaginably vast. At its peak, it stretched hundreds of thousands of kilometers across, a diffuse sphere of dust and gas larger than many planets. Its jets, already behaving strangely, would almost certainly react dramatically. Its dust, charged by sunlight and shaped by magnetic gradients, might scatter in complex arcs. Its inner coma, a region dense with ionized material, could be compressed violently by the CME's magnetic front. To solar physicists, this approaching storm was not a threat, it was a natural laboratory, a place where the sun's influence would reveal the unseen properties of interstellar matter. A chance to understand how objects formed beyond the solar system respond to the breath of a star they do not call home. The CME's signature appeared clearly in coronagraph imagery, a bright wavefront racing across the corona, expanding like an unfolding sail. Even from Earth's vantage, despite the eruption occurring on the far side of the sun, its edges shimmered through the solar limb with unmistakable clarity. The ejection's trajectory, slightly above the ecliptic, matched the orbital inclination of 3I Atlas with uncanny precision. Analysts noted with growing confidence that this was not a glancing pass. It was an encounter, and 3I Atlas, only recently awakened, seemed almost to anticipate the storm. Its coma brightened subtly in the days leading up to the CME. Jets sharpened in appearance. The diffuse halo swelled, as though pressure within the object's internal reservoirs was building. Whether this was influenced by the CME's approach or merely a coincidence of heating near perihelion, no one yet knew. But the visual transformation was undeniable. The visitor from the stars was shedding its icy silence, coming alive in a way that hinted at latent energies within. Some speculated that the CME might illuminate hidden aspects of the nucleus, cracks, vents, or structures that sunlight alone could not reveal. Others wondered whether the sudden influx of charged particles would generate electromagnetic emissions detectable by sensors monitoring the solar wind. A few even posited that the collision between the CME and the interstellar object might produce signatures unique to matter forged outside our solar system chemical fingerprints or plasma interactions unseen in local comets. But beneath all these questions lay a deeper, quieter recognition. This event, this unfolding intersection of cosmic paths, was not merely a scientific curiosity. It was a reminder of how dynamic, how alive, how interconnected the solar system truly is. The sun breathes storms into space, an interstellar object drifts into that breath, and a moment of profound scientific revelation becomes possible. The solar tempest is still on its path, expanding, cooling, yet carrying within it the energy of a star's restless surface. And 3I Atlas waits its tail unfurling, its jets awakening, its vast coma shimmering like a translucent shell. One wanderer born of the Sunday, one born of distant stars. Their meeting approaches. The space between the planets is not empty. It is threaded with invisible currents, streams of charged particles, rippling magnetic boundaries, and subtle gravitational tides. Objects drifting through this realm are shaped not only by their own mass and momentum, but by the delicate interplay of forces that reach across millions of kilometers. And in this woven landscape of dust, plasma, and light, geometry becomes destiny. The CME, now racing outward from the Sun, does not travel in a straight line. It expands as a three-dimensional wavefront, a balloon of plasma swelling outward into the heliosphere. Most of the time, this balloon stretches across space with little regard for the small bodies scattered through its path. Sometimes it brushes past an asteroid. Sometimes it compresses the magnetic field around a distant spacecraft. And very rarely, it intersects perfectly with a comet's orbit. But an intersection with an interstellar object, an object not born of this star, not shaped by its heat or magnetism, is almost unfathomably rare. For such an encounter to occur, dozens of conditions must align: the orientation of the object's hyperbolic path, the tilt of its orbital inclination, the timing of the CME's eruption, and the angle of the Sun's rotating magnetic field. These conditions, governed by independent processes, almost never overlap. Yet for three Atlas, they have. The CME launched from the far side of the Sun, but not deep from its backside. Instead, it erupted from a region still close to the solar limb, allowing coronagraph instruments to catch the event even as the eruption swept beyond direct view. At that moment, 3I Atlas sat at a position just slightly above the ecliptic plane, an inclination that, under most circumstances, would carry it out of the path of a standard CME, which tends to expand more strongly along the ecliptic. But this CME did not expand evenly. Its magnetic loops twisted upward, giving it a northward bias, a slight tilt relative to the solar equator. This upward movement aligned perfectly with 3I Atlas's position. When solar physicists modeled the CME's expansion across the inner heliosphere, its shockwave cut a path that swept directly through the coordinates of the interstellar visitor. If either body had been displaced by even a few degrees, the encounter would have weakened or vanished entirely. But the object's orbital inclination placed it exactly where the CME's energetic plume surged most strongly. The geometry, when visualized, resembles a cosmic choreography. The Sun turns, a sunspot erupts, a wave blooms outward, the object glides along its hyperbolic arc, and the two paths meet not by intention, but by the quiet mechanics of celestial motion mechanics that occasionally produce alignments so perfect they seem scripted. As models predicted impact, researchers began examining the phenomenon more closely. What they found heightened the significance of the event even further. Unlike most comets, which travel within or near the ecliptic plane, 3I Atlas approached the Sun along a distinctly inclined path. This unusual tilt meant that the CME's upper arc, typically the weaker region of the expanding shell, would strike the object not obliquely, but head-on. Simulated magnetic lines showed the CME enveloping 3I Atlas like a cresting wave passing over a stone. There would be compression at the front, turbulence along the sides, and a trailing wake as the CME passed. This geometry is not simply visually interesting, it determines the physics of the encounter. A CME carries with it not only mass, but magnetic structure. It pushes a shock front ahead of it, compressing the solar wind and raising its density. It drags tangled magnetic fields that can reconnect explosively with those around the body it contacts. It produces pressure, both kinetic and magnetic, that squeezes the coma of a comet like a giant, passing hand. If a CME hits a comet at a shallow angle, much of this energy disperses, but if it hits directly as this one is expected to, the effects can be dramatic. 3I Atlas, drifting with its enormous, newly awakened coma, lies in that direct path. The alignment is so clean that some researchers described it as surgical. The CME does not merely approximate the object's position at all, but envelopes it. And because 3I Atlas is slightly above the ecliptic plane, where fewer solar wind particles crowd the region, its coma is broader, lighter, and more fragile, making it even more susceptible to perturbation. But the geometry is not only about position, it is also about timing. The CME's projected arrival near 3I Atlas coincides with a period of heightened activity as the object nears its closest approach to the Sunday. This means the interstellar visitor is already venting material, already ionized by increasing solar radiation, already enveloped in a complex electromagnetic environment. CME interactions with dormant comets are one thing. Interactions with an already energized interstellar body are another. For space weather researchers, the approaching alignment evokes parallels to the Rosetta mission, but the similarities are superficial. Rosetta observed a controlled experiment, a spacecraft monitoring a known comet under well-studied conditions. But here, the experiment is natural, uncontrolled, and uniquely positioned in both geometry and timing. It is a meeting between a young solar eruption and an ancient alien traveler. As visualized in solar models, the CME's approach resembles an ocean storm cresting toward a solitary island. The vast shell of plasma expands outward, its brightest regions sweeping across interplanetary space. 3I Atlas drifts ahead, enveloped in a faint veil of dust and ionized particles. And in the center of the projection, where the model maps energy density and magnetic pressure, the interstellar object sits directly in the path of maximum intensity. For heliophysicists, the encounter is an opportunity to test models of plasma dynamics around bodies that do not originate from our heliosphere. The coma of 3ATLAS, ionized by the Sun but shaped by materials forged under different stellar conditions, could reveal departures from the plasma behavior seen in local comets. Dust particles with unusual compositions might charge differently. Magnetic boundaries might collapse or expand in unfamiliar ways. All of this stems from geometry alignment in space, orientation in orbit, timing in motion. But the geometry carries another implication, one far more visual. Observers across Earth may witness the aftermath. Because 3I Atlas is now emerging from behind the Sun, shifting into a position where Earth-based telescopes can observe it more clearly, the tail and coma are becoming increasingly visible. After the CME impact, if the geometry is sufficiently direct, astronomers may witness a phenomenon known as a tail disconnection event, a sudden, dramatic severing of the ion tail, which then drifts away before reforming. This can occur when the magnetic field carried by a CME collides with the magnetic environment surrounding the comet, snapping the connection like a tensioned thread suddenly cut. Photographers, amateur astronomers, and space agencies around the world may capture this event, a real-time visualization of the Sun's magnetic and plasma environment interacting with an alien body. For NASA, this geometry is more than chance. It is a scientific gift. It allows researchers to model CME interactions under conditions impossible to create artificially. It bridges heliophysics with planetary science, dust-plasma interactions with interstellar studies. It gives scientists a laboratory composed not of equations and controlled environments, but of cosmic choreography unfolding naturally in the vacuum of space. And for humanity, it offers something subtler, a moment where we witness two wanderers, one born of our sun, one traveling from the distant dark meeting in silence, guided only by the geometry of space and time. The CME continues outward. 3I Atlas drifts forward. Their paths are set, their meeting approaches. And when the storm reaches the interstellar traveler, the universe will reveal yet another layer of its quiet, intricate design. If the geometry of the CME's approach set the stage, The environment surrounding 3I Atlas became the chamber in which the true mystery unfolded. For all of its strangeness, its jets, its coma, its erratic brightening, the most unsettling aspect of the interstellar visitor lay not in its outward appearance, but in the invisible forces that shaped it. Forces that whispered of complex plasma physics, electromagnetic gradients, and dust behaviors seldom observed in bodies native to the solar system. To understand why scientists found 3I Atlas so perplexing, one must consider what happens to any comet as it nears the Sunday sunlight strikes its frozen nucleus. Volatiles, water, carbon monoxide, ammonia evaporate into gas. Dust grains lift away from the surface. These materials form a coma, a diffuse envelope of dust and ionized gas that interacts with the solar wind. Magnetic fields surrounding the comet arise not from the comet itself, but from the way charged particles are organized around it. But this familiar pattern is not what researchers observed with the interstellar object. Instead, the plasma surrounding 3I Atlas behaved as though it were part of a complex, active system, one that bore similarities to dusty plasma experiments conducted on Earth in laboratory chambers, but scaled to astronomical proportions. A system whose emergent patterns suggested a delicacy and responsiveness rare for a small, tumbling body drifting in sunlight. The first clue lay in the structure of the coma. Comae of typical comets blur outward in soft gradients. Their densities fall smoothly with distance. Their ions flow along solar magnetic fields in ways that can be predicted and modeled with relative ease. But 3I Atlas's coma did not diffuse evenly. Instead, faint ridge-like patterns appeared, zones of enhanced density separated by narrow, filament-like voids. Some of these ridges curved gently, as though shaped by shearing plasma flows. Others stretched radially, pointing away from the nucleus as if guided by invisible rails. The organization was subtle, so faint it required stacked long-exposure images to detect. But once seen, it could not be dismissed. This was dust plasma structuring behavior normally produced when charged dust interacts with electric fields, forming self-organizing patterns similar to those in laboratory dusty plasma rings. But observing such structuring around a comet was rare. Observing it around an interstellar object was unprecedented. Further anomalies appeared in the behavior of the jets. In ordinary comets, jets emerge from regions warmed unevenly by sunlight. They twist and diffuse as the comet rotates. Yet around 3I Atlas, several of the jets remained rigid in their orientation far longer than physics typically allows. Even as the nucleus rotated on its slow 16-hour cycle, their directionality persisted. It was as though the jets were not merely streams of sublimating gas, but guided currents, channeled along stable pathways created by electromagnetic fields within the coma. The nucleus, small and uneven, could not provide such guidance on its own. Only the larger-scale plasma environment could. And so scientists began studying the plasma shell surrounding the object, the ionopores, the bow shock, and the magnetic cavity that formed around it as the solar wind rushed past. In many comets, these boundaries behave predictably. But in 3I Atlas, the distances between these layers seemed exaggerated, as though charged particles were being drawn into unexpectedly broad regions. Charged dust, when interacting with a strong or unusual plasma environment, can amplify electromagnetic features dramatically. This amplification could explain why some jets drifted little even during rotation. It could explain the faint structural channels threading through the coma, and it could explain why the object's anti-tail appeared more distinct than models predicted. The anti-tail, in fact, became a focal point of discussion. Usually, an optical illusion produced by viewing geometry An antitail is composed of larger dust particles lingering behind the comet's orbital plane. But the antitail of 3I Atlas behaved with unusual coherence, sharp, narrow, persistent. Some researchers proposed that electromagnetic sorting was segregating dust by charge and mass, causing heavier grains to remain in aligned sheets guided by plasma gradients. Such behavior hinted at something profound. 3I Atlas's dust might be fundamentally different from the dust in solar system comets. Over millions or billions of years drifting through interstellar space, cosmic rays may have altered the grains. Radiation could have pierced their molecular structures, changing how they ionize. Magnetically active metals or exotic mineral phases might charge differently under solar exposure. If so, then the plasma around 3I Atlas was not simply active, it was alien, shaped by materials forged under the light of distant suns. Then came the question of outgassing chemistry. Spectral analysis from ground-based telescopes detected familiar signatures: water vapor, carbon-bearing volatiles, but in proportions that shifted unpredictably. On some nights, the object brightened in emissions normally associated with CO2. On others, water dominated. At times, the brightness and ratios defied temperature expectations entirely. Comets from the solar system display variation, but this level of inconsistency hinted at deeper complexity. Some speculated that 3I Atlas's nucleus contained layered shells, each formed under different conditions during its long interstellar journey. Others suggested fractured reservoirs where pockets of volatile material were trapped beneath ancient crusts until destabilized by solar heating. Still others hypothesized that cosmic ray exposure had altered the molecular structure of the ice itself, creating compounds that sublimated in nonlinear patterns. The plasma structure also hinted at magnetization behaviors, uncommon in local comets. While comets do not possess intrinsic magnetic fields, the interaction between their charged environments and the solar wind can induce temporary magnetic cavities. With 3I Atlas, the cavity appeared unusually large, far more inflated than expected for an object with such a small nucleus. This inflation suggested that ionized dust was playing an oversized role. Dusty plasma physics teaches that when particles carry both mass and charge, they can create collective effects that dramatically alter the plasma environment. They can create gradients, filaments, voids. They can shape how magnetic fields wrap around the body. And when influenced by the solar wind, they can respond in ways far more complex than gas alone. Thus emerged a radical but scientifically grounded idea. 3I Atlas was not merely a comet, it was a dusty plasma organism, a structured environment formed by alien dust interacting with solar forces. This did not imply consciousness or artificial construction. It simply meant that the object's behavior was governed by a physics more intricate than the standard sublimation outgassing model applied to comets of the solar system. Its plasma envelope, shaped by dust with interstellar histories, was reacting to the sun in ways that our models could not yet fully capture. And all of this complexity, these ridges, filaments, jets, cavities, was unfolding before the CME arrived. Scientists knew that once the solar storm struck, the object's delicate plasma structure would be tested. Would it collapse, strengthen, twist into new forms? Would the jets reorient? Would the tail sever? Would the anti-tail dissipate or grow sharper? No model could say for certain. The only certainty was that the interstellar object, already alive with electromagnetic tension, was about to be struck by the full force of a solar tempest. Two environments, one alien, one familiar, would meet, and in their meeting, the unknown would blossom. As the interstellar traveler continued its slow descent toward perihelion, its transformation became unmistakable. What had once been a faint, ambiguous smear drifting through the telescope images of early observers now unfolded into a complex, luminous being, alive with motion, structure, and change. It was not merely growing brighter, it was awakening, revealing layers of activity that suggested a body long dormant now stirred by the unfamiliar warmth of a new star. The earliest signs of this awakening were subtle: a slight intensification in the coma, a faint elongation along one axis that hinted at a nascent tail. But as the object descended into regions of stronger sunlight where photons strike harder, where the solar wind grows denser, the subtlety vanished. In its place rose a vibrant display of jets, filaments, and shifting clouds of dust and gas. This was the true beginning of 3I Atlas's visible life within the solar system. The coma swelled first. From a muted envelope wrapping the small nucleus, it blossomed into a vast sphere of dust and vapor. Estimates placed its radius at several 100,000 kilometers, larger than gas giants, larger even than the diameter of the Sun when fully expanded. Few comets in the solar system ever achieve such dimensions, and those that do typically require intense outbursts or exceptional reservoirs of volatile material. Yet 3I Atlas had begun expanding long before it drew close to the Sun, suggesting that its internal composition was primed for reaction. Within this coma, threads of brightness emerged, jets bursting from the nucleus like luminous veins threading through a translucent shell. They appeared not as chaotic plumes, but as structured conduits, narrow paths of dust and gas that revealed the presence of active vents or fractures within the nucleus. Some of these jets twisted subtly as they extended outward, curling under the influence of solar radiation pressure. Others remained remarkably straight, as if guided along electromagnetic channels in the surrounding plasma. The presence of these jets signaled one undeniable truth: 3I Atlas was shedding mass, rapidly. This shedding did not imply decay, not yet. Rather, it was the natural expression of awakening. Comets, like seeds lying dormant beneath centuries of ice, ignite into life when touched by light. Interstellar objects are no different, though the materials they carry may respond in unfamiliar ways. The jets of 3I Atlas, however, carried a distinct personality: patterns of activity that rose and fell with irregular rhythms, as though the nucleus exhaled unevenly. Observers noted a particularly striking jet pointing sunward, forming what many described as a downward-facing plume. This defied expectations. Sunlight usually drives material away from the Sun, not toward it. Yet 3I Atlas's sunward jet behaved like an anti-tail, a structure formed when heavy dust particles remain in the orbital plane as the object passes through sunlight. But this structure was more than an optical effect. It held coherence, shape, and singular brightness, suggesting that it was not merely lagging dust but an active jet, venting material forward toward the solar disk. Such a feature indicated that the nucleus's internal morphology, its fractures, pockets, and volatile reservoirs, was deeply uneven. Light reached some pockets earlier than others. Thermal waves permeated its crust in complex patterns, activating vents at unexpected times. The result was a visually stunning array of jets that gave the coma the appearance of a breathing, shifting organism. Then came the tail. At first faint and nearly invisible, the tail began forming after the object passed behind the Sun relative to Earth, emerging into viewing conditions where its lateral structure could be seen more clearly. What had once appeared as a dim extension transformed into a sweeping filament stretching vast distances into space. Amateur astronomers, using long exposure stacking techniques, captured the tail fanning outward with increasing clarity threads of ionized dust and gas glowing faintly in the darkness. Some observers reported multiple tails, a primary ion tail, a dust tail, and the enigmatic anti-tail. These structures glowed differently, revealing their separate compositions and interactions with solar radiation. The ion tail, shaped by the solar wind, lifted outward in a long, straight line pointing opposite the sunday. The dust tail curved gently, sculpted by radiation pressure, and the anti-tail, still sharp, still unusual, traced a thin blade-like structure sunward. Such complexity is not impossible for comets, but it is rare, and coming from an object of interstellar origin, it raised questions. Why did 3I Atlas possess such distinct and stable structures? What materials composed its dust? How did its plasma environment maintain coherence despite its slow, tumbling rotation? The coma's luminosity also shifted in unexpected ways. In some exposures, the inner coma gleamed with concentrated brightness, suggesting sudden increases in outgassing. In others, the outer coma faded asymmetrically, hinting at directional dust release influenced by both solar heating and plasma gradients. These fluctuations did not match the regular cycles seen in typical comets. They were erratic, almost pulsatile, as though the object's internal layers responded to sunlight, unevenly activating in bursts as temperature thresholds were crossed. Instrumentation added further intrigue. Spectral data indicated variability in the chemical signatures of the outgassed material. Water vapor appeared strongly in some observations, weakly in others. Carbon-bearing gases fluctuated in patterns that puzzled researchers. Some nights saw a marked increase in certain emissions, others showed abrupt declines. This chemical inconsistency suggested either layered reservoirs within the nucleus or volatile materials arranged in complex pockets. Long-term storage in interstellar space subjected to cosmic rays, high-energy particles, and the cold of the galactic medium may have altered the internal structure of the nucleus, creating volatile-rich veins and radiation-scarred crusts. As the sun's heat penetrated these layers, each responded in its own way, producing a cascade of emissions that made the comet appear to breathe. This awakening reached its peak in the days leading up to the CME impact. The coma grew brighter, the jets sharpened, the anti-tail extended. Observers noted flashes of internal activity, tiny bursts of light that suggested small outbursts within the nucleus. Some speculated that pockets of volatile gases were reaching critical temperatures and venting suddenly. Others proposed that the object's rotation brought active regions into and out of view, producing sudden visual changes. And then came the most curious development. The coma thickened, not merely expanding in size but increasing in density near the nucleus. This thickening may have indicated that the object's internal reservoirs had become more volatile, or that its crust was fracturing under thermal stress, releasing larger quantities of dust. It may also have been influenced by the solar wind, which had become increasingly erratic as the CME advanced through interplanetary space. Whatever the mechanism, the effect was unmistakable. 3 Atlas was no longer a quiet traveler. It had become a vibrant, reactive, dynamic presence, a body in transition, responding to forces it had not encountered in millions of years. And this awakening was only the prelude, because as the sun's storm barreled toward it, the interstellar object, alive with jets, dust, plasma, and light, was poised to undergo a transformation driven not only by sunlight, but by the full force of a solar eruption. The awakening was only beginning. The true test was yet to come. The deeper astronomers looked into the behavior of 3I Atlas, the more the slow, tumbling motion of its nucleus emerged as a key to its strangeness. A rotation period of roughly 16 hours is not unusual for a cometary body Some rotate more quickly, others far more slowly, but the behavior surrounding 3I Atlas did not reflect that rhythm. It behaved instead as though its rotation were disconnected from the activity unfolding around it. The jets did not smear. The plasma did not swirl in patterns consistent with a spinning nucleus. The dust structures remained strikingly stable, as if indifferent to the turning of the object at their center. And so the 19-hour light curves, painstakingly assembled through repeated exposures and careful stacking by skilled observers, revealed something essential. 3I Atlas was rotating, yes, but its rotation alone could not account for the complexity and persistence of its structured jets. It was tumbling, not rotating about a single stable axis, but precessing, wobbling, drifting through space like a fragment of ancient stone unsettled by its own asymmetries. Tumbling is common among small bodies, particularly those of irregular shape, but tumbling typically produces certain signatures: jets that twist around the nucleus, dust emissions that blur into spirals, coma that exhibit asymmetry synchronized with rotational timing. Yet here, the signature was faint. The jets should have been smeared into soft, rotating plumes. Instead, they held their coherent structure longer than expected. If one imagined 3I Atlas as a lantern suspended in a vast, invisible wind, one might expect the beams of light to sweep across the environment with each wobble. But instead, the beams, those narrow jets, seemed locked into position, guided by forces beyond the rotation of their source. This mismatch raised the first profound question. If the nucleus is rotating, why aren't the jets rotating with it? Several hypotheses emerged. One suggested that cavities within the nucleus tubes, carved through ice and rock by trapped gas, were so deep and narrow that the rotation of the surface did not significantly alter the orientation of their outflows. But this required that those cavities be almost perfectly aligned with the object's moment of inertia, a coincidence so unlikely that most researchers dismissed it. Another hypothesis invoked electromagnetic confinement, the idea that once dust and ions were ejected, they were trapped or funneled into stable channels by electric fields within the coma. Such a mechanism could allow jets to hold their shape even as the nucleus rotated beneath them. It would also explain the appearance of braided filaments and faint plasma ridges spiraling through the coma. A third hypothesis posited uneven mass loss, such that outgassing created torque impulses that altered the spin state irregularly. If the rotation were evolving rapidly, accelerating or decelerating as internal volatiles shifted, then the external structures might not reflect a stable rotational signature. But observational data suggested that the rotation rate was, in fact, relatively consistent over time, making this explanation insufficient on its own. And then there was the fourth hypothesis, bold, speculative, and yet grounded in real physics. The jets were not responding to rotation because they were responding to the solar wind. In this view, the nucleus provided the raw material gas, dust, ions, but the orientation and persistence of the jets were shaped primarily by electromagnetic gradients in the surrounding plasma environment. The solar wind, interacting with ionized dust, created a network of pathways, filaments, and pressure boundaries. Once material entered these channels, it flowed along them rather than dispersing freely. The jets, in this sense, were less like vents and more like currents within a sculpted plasma river. Such behavior is not science fiction. It is known to occur in dusty plasma experiments, where charged particles self-organize into chains and filaments. It has been observed, faintly, around comets such as 67P, yet the scale required around 3I Atlas, hundreds of thousands of kilometers, was unprecedented, suggesting that the object's dust carried properties distinct from typical cometary material. which led to a deeper question. What was the dust made of? Spectral data remained ambiguous. Some lines indicated water-ice sublimation, particularly closer to perihelion. Others suggested carbon-bearing volatiles. But the dust carried behaviors that hinted at more exotic origins. Grain charge may have been higher than expected. Ionization levels fluctuated beyond norm. Charged dust clusters, once formed, appeared unusually resilient to diffusion. These properties mattered because charged dust interacts strongly with magnetic fields, even weak ones, and the solar wind is not uniform. It contains gradients, shocks, and pockets of instability. If 3I Atlas's dust responded intensely to such features, the jets could stabilize into rigid structures independent of the nucleus's rotation. Meanwhile, the nucleus itself continued its slow, tumbling motion, wobbling through space in a pattern that spoke of irregular mass distribution. Some researchers speculated that the nucleus might be elongated or lumpy, with pronounced lobes or ridges. Others suggested that it could be fractured, a cluster of bonded fragments rather than a single monolithic body. But the most important insight came from the combined evidence of rotation and jet stability. 3ATLAS was not simply outgassing, it was interacting with the solar environment in a manner shaped by both its internal composition and the external plasma conditions. The 16-hour rotation period played a role, but not the dominant one. It turned the nucleus like a slow gear, exposing pockets of volatile material, shifting stresses, altering the pressure of gases trapped beneath the surface. But the external plasma-charged dust, magnetic fields, solar wind acted as the larger system, shaping the jets long after they left the nucleus. This interplay created the most visually striking phenomenon of all, the persistence of structured jets over multiple rotations. Even as the object tumbled, the larger-scale plasma environment held some jets in place, guiding them through electromagnetic corridors. It was as though the object were exhaling into an invisible architecture that shaped each breath into form. This dynamic produced the illusion that the jets were locked to a particular orientation, when in reality they were locked to the environment surrounding the object itself. As the CME drew closer, scientists watched these structures intently. The approaching solar storm carried a magnetic field thousands of times stronger than the ambient solar wind. Its shock front would crash into 3I Atlas's fragile, filament-rich plasma environment like a tide hitting a web of smoke. Would the 16-hour rhythm shatter under the impact? Would the plasma channels collapse, dispersing the jets into chaos? Would new pathways form, driven by the magnetic turbulence of the CME? No one knew. The rotation of the nucleus offered few clues. The jets offered only their stubborn persistence. The plasma environment, alive, vast, and delicate, prepared itself, knowingly or not, for its first encounter with a solar storm. The interstellar traveler continued its slow spin, indifferent to the anticipation around it, and the universe waited for the moment when the breath of a star would strike the pulse of an object that had wandered through darkness for millennia. Long before human eyes were capable of witnessing such events, the universe had been shaping encounters between comets and solar tempests. The meeting of a coronal mass ejection with a fragile body of dust and ice is not a collision in the conventional sense. It is a sweeping transformation, a sculpting of plasma and dust by forces too vast to be resisted. Yet never in recorded history has such a confrontation involved material born under another star. And as the CME surged toward 3I Atlas, its wavefront broadening, its magnetic field lines unfurling like banners of invisible fire, scientists understood that they were about to witness the first interstellar experiment conducted by the Sun itself. What happens when a CME strikes a comet has been studied before, most famously during the Rosetta mission. When a solar storm collided with comet 67P Churyumov-Gerasimenko, the magnetic field surrounding the nucleus surged from tens of nanotesla to several hundred in mere moments. The bow shock compressed. The ion tail snapped like a rope whipped in a storm. Dust swirled violently, reorganized by sudden electromagnetic shifts. Instruments captured a chaos of signals as electrons, ions, and dust particles reacted to the incoming front. Yet, even this dramatic event paled when compared to the scale of what astronomers expected from 3I Atlas. Its coma was colossal, much larger than 67P's. Its dust carried unusual charge properties. Its jets were arranged in structured channels, and its plasma environment appeared unusually sensitive to changes in the solar wind. The CME approaching it was significant, though not extraordinary by solar standards. But when a precise alignment, an awakened interstellar object, and an emerging solar storm intersect, the result becomes something altogether unprecedented. To understand how the impact would unfold, one must first consider the three layers of the interaction. The magnetic shock front. Ahead of every CME travels a region of compressed plasma, a shock wave where the solar wind intensifies, becomes denser, and heats abruptly. When this shock hits a comet, it can compress the plasma cloud surrounding it, pushing the magnetic cavity inward. In extreme cases, this compression becomes so intense that the comet's ion tail, long, thin, delicate, is severed cleanly and swept away by the turbulent flow. These tail disconnection events are among the most visually dramatic consequences of CME impacts. A comet's glowing ion tail suddenly detaches and drifts into space as the nucleus forms a new one behind it. Many observers hoped, and some quietly suspected, that 3I Atlas might undergo such an event. Its ion tail, already unusual, seemed delicate enough that even a modest CME could shear it apart. But 3I Atlas was not an ordinary comet. Its anti-tail, dust jets, and plasma channels formed a complex network that might respond differently from known bodies. Some scientists proposed that instead of a simple disconnection, the CME might generate multiple breakpoints in the ion tail, or scramble the structured jets into new configurations. Others speculated about a dramatic brightening, a burst of activity triggered by rapid changes in pressure and magnetic fields. The magnetic field of the CME. Behind the shock front lies the body of the CME itself, a vast, swirling mass of magnetic fields and charged particles. When these fields reach a comet, their interaction with the local plasma can trigger reconnection events, moments in which magnetic field lines snap and reconnect, releasing bursts of energy. For 3I Atlas, these interactions posed particularly intriguing possibilities. Its dust grains, possibly carrying higher than normal charges, could respond dramatically to sudden field reversals. Its jets, guided by existing plasma channels, might twist or collapse entirely if those channels destabilized. Its coma might expand unevenly, forming asymmetric wings of dust and gas. The magnetic cavity around it, already inflated beyond expectations, might shrink violently, causing turbulence that could expose deeper layers of the nucleus. Such reactions would not only reshape the object's appearance but reveal the physics governing its dust and plasma environment. The physical pressure of the CME. Though CMEs carry immense numbers of particles, their density remains extremely low compared to matter on Earth. Yet for a comet, this flow represents substantial force. The dust tail, so vast and diffuse, is especially vulnerable. The CME's pressure could flatten the ion tail, pressing it sideways relative to the sunday, bend the dust tail into a curved arc, rip apart delicate dust structures formed during the object's awakening, accelerate or redirect charged particles within the coma. The sunward-facing jet, already a source of fascination, might elongate, collapse, or flare under the sudden change in plasma pressure. If it truly was shaped by electromagnetic sorting, the CME could expose the underlying physical processes, revealing whether the jet was merely dust flowing along an optical alignment or a genuine, stable, electromagnetically guided structure. What happens beneath the surface? A CME's influence does not end at the coma. It can penetrate deeper, transferring energy indirectly into the nucleus itself. While the CME does not strike the nucleus physically, the rapid changes in plasma and magnetic pressure can alter the thermal and mechanical stresses within the surface layers. Jets may intensify or flicker out. Surface crusts may crack. New vents may open. The 16-hour rotation period could be disrupted if mass loss becomes uneven. Changes in torque might accelerate or slow the spin. In extreme cases, fractures could propagate through the nucleus, leading to fragmentation events. Astronomers did not expect 3I Atlas to break apart. It showed no signs of internal instability, but the possibility could not be fully dismissed. The first moment of impact. When the CME finally reached the interstellar object, its arrival would be almost silent, no sound, no flash visible from afar. Instead, the changes would unfold through instrumentation, a sudden brightening, a shift in plasma density, a spike in emissions as ions accelerated. The ion tail might twist abruptly, the dust tail might flare outward, the jets might distort or reform. Because the impact region lay beyond Earth's line of sight until recently, observations would come from multiple vantage points, ground-based telescopes, amateur astronomers, spacecraft, and solar monitoring instruments. The unfolding of the CME's effects on 3I Atlas would be captured in a mosaic of data, images, spectra, photometry, and plasma measurements. But one thing was certain: even a modest CME, arriving at the right moment, could reshape the interstellar traveler dramatically. And this was no ordinary moment. The object had awakened. Its coma was dense. Its plasma environment was alive. Its dust was electrified. The CME would not simply pass over it. It would test it, stress it, reveal it. The aftermath would tell astronomers more about the object than weeks of observation could have. Would the ion tail sever cleanly? Would the anti-tail dissolve or strengthen? Would the nucleus brighten, dim, or fracture? Would the jets twist into new orientations? Would the plasma architecture collapse into chaos or reorganize into new forms? The interstellar visitor, after millions of years wandering alone, was about to be reshaped by the breath of a star it had never known. In this moment, not catastrophic, not violent, but transformative, the universe would reveal clues about how alien dust, ancient ice, and interstellar plasma respond to the storm of a foreign sun. By the time the CME closed the final span of interplanetary space, it had already ignited a storm of speculation among scientists. Not the sensationalism found in rumor or fringe theories, but the sober, intricate puzzles that arise when data refuses to align cleanly with established models. Theories blossomed across research groups, some elegant, some coarse, all striving to reconcile the mounting contradictions that 3I Atlas presented. What troubled researchers most was not any single anomaly, but the constellation of them: the oversized coma, the coherent jets, the persistent anti-tail, the rotation, independent structures, the erratic chemical emissions, the inflated magnetic cavity, and the plasma filaments so faint and delicate they seemed almost biological in their complexity. In isolation, each phenomenon could be explained by known physics. Together, they formed a picture that did not comfortably fit within any single theoretical framework. The standard comet model under strain. The first and most obvious explanation was simply that 3I, Atlas, was a comet, albeit a strange one. It could be rich in volatile materials, fractured from a larger body, or bearing unusual dust grains sculpted by millions of years in the interstellar medium. But each time scientists attempted to force the object into the standard model, discrepancies emerged. In particular, its coma awakened too early for a comet that was still distant when first observed. Its jets held unnatural coherence, resisting diffusion even as the nucleus tumbled. Its dust displayed excessive charge sensitivity, implying grain structures not typical of solar system comets. Its plasma cavity inflated far beyond predictions, suggesting unusually dense ionized dust. Standard models could explain some of this, but no single model could explain all of it simultaneously. Theories began branching into new territory. The interstellar chemistry hypothesis. One of the earliest and strongest proposals came from astrochemists who believed that the key to 3I Atlas lay not in its dynamics, but in its composition. Interstellar space is rich in cosmic rays, relentless, penetrating, destructive. Over millions of years, these high-energy particles can alter molecular structures profoundly. Complex organics fracture, ices reorganize, dust grains accumulate electrostatic scars, materials become porous, metastable, chemically reactive. Some researchers believed that 3I Atlas carried radiation-sculpted volatiles that behaved unpredictably when warmed. Ices may sublimate at unusual temperatures. Dust grains might hold or release charge erratically. Pockets of altered chemistry could trigger sudden jets or asymmetrical outbursts. This hypothesis could explain the erratic spectral signatures and the pulsatile behavior of the jets. It could even explain the vast coma if the nucleus carried materials that sublimated more readily than typical cometary ices. But it did not explain the electromagnetic structuring of the jets. The dusty plasma framework. Next came the plasma physicists. To them, 3I Atlas resembled not an inert comet, but an active dusty plasma body, a cloud of charged dust grains interacting with solar wind and magnetic fields in ways more reminiscent of laboratory plasma rings than of celestial bodies. In dusty plasma systems on Earth, particles self-organize into filaments. Electric fields create channels through which dust flows. Magnetic gradients sculpt lanes of coherent structure. Dust aligns into braided streams under oscillating plasma pressure. These behaviors are delicate, rare in astronomical settings, yet entirely possible under the right conditions, particularly if the dust grains carry unusual charge or shape characteristics. For plasma physicists, the behavior of 3I Atlas made sense. The coherent jets could be electromagnetic conduits. The anti-tail could be a charged dust sheet shaped by solar wind pressure gradients. The inflated magnetic cavity could be the result of dust-dominated plasma interactions. The filamentary coma could reflect self-organized plasma structures on a massive scale. This theory was compelling, but it raised another question. Why would an interstellar object possess unusually charge-responsive dust? For that answer, scientists turned toward its origin. Planetary fragment hypotheses. Some researchers suggested 3I Atlas might be a fragment of a shattered planetesimal, a small primitive body, sculpted in the early days of a distant star system. If so, its dust may contain minerals uncommon in our solar system, including iron-rich silicates, carbonaceous compounds with altered charge dynamics, exotic crystalline forms, rare oxides shaped by ancient stellar environments. If such materials were charged or structured differently, their plasma interactions could be dramatically amplified. One theory suggested that 3I Atlas came from a young, active star system, where radiation and frequent flares sculpted its chemistry. Another posited that it originated from a system undergoing early planetary migration, where gravitational instabilities could fling debris into the galactic medium. A third, more speculative proposal suggested tidal stripping, that 3I Atlas might be a slab or shard torn from a larger body during a close pass around its parent star. Such an event would fracture the object internally, leaving caverns and reservoirs that would later vent dramatically when warmed. These models explained the uneven outgassing and strange internal structure, but they did not fully account for the persistent electromagnetic shaping of the jets. Hybrid models. As data accumulated, many scientists converged on hybrid models, combinations of interstellar chemistry, dusty plasma physics, and exotic mineralogy. In these frameworks, 3I Atlas was not extraordinary because of a single property, but because of many properties interacting simultaneously. The hybrid scenario suggests a nucleus rich in volatile ices altered by cosmic rays, dust grains with unusual charge to mass ratios, plasma channels forming self-organizing structures in the coma, a slow, tumbling rotation that exposes vents irregularly, an anti-tail shaped by ionized dust slabs, jets guided by electromagnetic gradients rather than nucleus geometry. In this view, 3 Atlas was not breaking the rules of physics, it was revealing corners of physics rarely accessible in natural settings. The exotic hypothesis, still scientific. A minority of researchers proposed something bolder, though still grounded in astrophysics, that 3I Atlas might have originated in a binary star system. Binary systems produce extreme environments, chaotic gravitational fields, tidal forces that fracture small bodies, radiation environments that produce exotic chemistry, plasma fields unlike those around single stars. If 3I Atlas formed in such a system, its dust and ice composition might reflect conditions impossible near solitary stars like the Sun. This could explain the complex interactions observed in its coma and its sensitivity to solar wind variations. Speculative theories and their boundaries. Beyond conventional science, some speculated about artificial origins, an idea fueled by the media fascination surrounding Oumuamua. But unlike that enigmatic visitor, 3I Atlas exhibited clear signatures of outgassing, dust jets, and natural cometary behavior. It was unquestionably a natural body, albeit an unusually complex one. In the scientific community, such exotic ideas remained outside the realm of evidence. The unifying theme, incomplete understanding. Ultimately, the leading theories converged on a humbling recognition. 3I Atlas was showing humanity something new. Not supernatural, not impossible, simply unknown, a region of physics rarely observed in natural objects. Theories would continue to evolve after the CME impact, as the solar storm reshaped the interstellar traveler and exposed new facets of its nature. Each hypothesis, cometary, interstellar, plasma-driven, or hybrid, would be tested by the storm's arrival. Because when the breath of the sun met the dust of distant stars, the truth of 3I Atlas would begin to reveal itself in ways no theory alone could predict. Long before the public announcement, long before the live stream page appeared with its quiet promise of revelation, NASA's instruments had already been watching. While the agency remained outwardly silent, calm, cautious, measured, its fleet of observatories had been gathering the raw materials that would become the most complete portrait ever made of an interstellar object under solar influence. Every pixel, every spectrum, every faint whisper of reflected light became part of a growing tapestry of data. And now, with the CME closing in, NASA prepared to reveal what it had seen. The agency's approach was deliberate. This was no ordinary comet and no ordinary observation campaign. It was an event that blended the disciplines of heliophysics, planetary science, plasma physics, and astrophysics into a single unfolding experiment. To study 3I Atlas truly study it, the agency drew upon every available tool across the solar system. The Hubble Space Telescope. Hubble had been among the first to secure high-resolution images of 3I Atlas. Though the object appeared only as a luminous haze wrapped around a tiny core, Hubble's sensitivity allowed teams to estimate the nucleus's size. Early measurements suggested a diameter of around 2.8 kilometers, though uncertainties remained large. The coma's brilliance scattered light, blurring the nucleus, forcing analysts to model its size indirectly through brightness and thermal behavior. Hubble's ultraviolet and visible light observations also revealed hints of the object's composition. Emission lines consistent with water, carbon monoxide, and other volatiles appeared faintly, but these signatures were inconsistent, rising and falling unpredictably. This fluctuation hinted at internal reservoirs, venting in spurts rather than in continuous flows. The images were breathtaking not for their clarity, but for their puzzle-like nature snapshots of an object that refused to behave predictably. High-rise on the Mars Reconnaissance Orbiter. Perhaps the most anticipated imagery came from an unexpected source, the high-resolution imaging science experiment, HiRISE, camera orbiting Mars. With its powerful optics, capable of resolving objects at astonishing distances, HiRISE captured 3I Atlas from the vantage point of another planet free from Earth's atmospheric interference and in a geometry that provided an angle impossible from home. The images, taken on October 3, underwent extensive calibration, dust corrections, radiation noise removal, motion compensation. Only after weeks of processing did a faint but distinct shape emerge. Not a crisp nucleus, but a point wrapped in a faint, structured coma with hints of jet alignments radiating outward. Though the resolution could not unveil the nucleus directly, it provided crucial details. A probable asymmetry in the coma near the nucleus, evidence of vent-like structures guiding the jets, confirmation that the antitail was a real dust feature, not an imaging artifact. These details, subtle, exquisite, formed the backbone of NASA's internal analyses. SOHO, stereo, and solar observing missions. The sun-watching spacecraft SOHO, Stereo A, Stereo B, Parker Solar Probe were essential for mapping the environment through which 3I Atlas drifted. Their coronagraphs recorded the CME eruption from the moment it rose from the solar limb. Their particle detectors measured the velocity, density, and magnetic structure of the storm. These missions allowed scientists to model the CME's estimated arrival time, predict the shock front's strength, anticipate changes in solar wind speed and density, map the magnetic polarity of the incoming plasma. For the first time, astronomers would be able to compare an interstellar object's response to a solar storm with a detailed record of the storm's structure, a pairing that promised unprecedented insight. Ground-based observatories. Across Earth, observatories large and small contributed to the mosaic. From Chile's Atacama Plateau to Hawaii's Mauna Kea to Spain's Roque de los Muchachos, telescopes recorded 3I Atlas as its coma brightened. Spectrographs analyzed its chemistry. Photometric surveys monitored changes in brightness and jet orientation. But just as important was the global network of amateur astronomers. Their stacked exposures, painstakingly assembled over nights of careful imaging, revealed tail structures that no single observatory could capture continuously. Some provided hundreds of exposures over weeks. Others captured the anti-tail at angles unavailable to large telescopes constrained by schedules or weather. Their data offered a timeline of change, a living record of the interstellar traveler's awakening. NASA scientists prepare for the reveal. Behind the scenes, hundreds of researchers analyzed the incoming images. Teams met daily to cross-reference datasets. Plasma physicists comparing coma structures to solar wind conditions. Planetary scientists modeling internal venting based on jet orientations. Dust specialists analyzing the grain-size distributions and scattering behavior. Heliophysicists forecasting CME interactions with incredible precision. In their hands, the interstellar object became less a celestial curiosity and more a complex physics problem, a natural experiment unfolding across millions of kilometers. Every image mattered. Every spectrum held meaning. Every shift in brightness carried clues. For weeks, NASA held the data close not out of secrecy, but out of scientific caution. Misinterpretation could mislead. Early assumptions could mischaracterize. Interstellar objects are rare. Accuracy was essential. Now, at last, the time had come. The live stream announcement served as a quiet signal. The data had stabilized, the analyses had converged, the story was ready to be told. NASA planned to reveal Hubble imagery showing coma structure at various development stages, high-rise images offering new angular information, spectral data revealing volatile fluctuations, rotation models tracing the object's 16-hour tumble, CME trajectory predictions showing the precise alignment with 3I atlas. They would not offer speculation, they would offer measured truth, what the data showed, no more, no less. And beneath this steady voice lay a deeper anticipation. The storm would strike soon. The interstellar traveler, awakened and fragile, would respond. NASA's instruments scattered across space, perched atop mountains, orbiting distant worlds, would capture the event in real time. The reveal was not the end of the story. It was the threshold. A moment before transformation, a quiet breath before the sun reached out in full force. The interstellar visitor awaited the storm. NASA awaited the data, and the world awaited the unveiling of what lay hidden within the luminous shroud of 3I Atlas, its origin, its nature, its mysteries finally stepping into the light. Long before NASA's live stream countdown began ticking across screens, long before experts assembled their carefully worded statements and models, the interstellar traveler had already become something else, something more profound than a scientific object studied from afar. It had become a shared sight, a point of connection between thousands of eyes scattered across Earth, who sought it through the quiet clarity of night. For decades, the story of distant cosmic visitors belonged almost exclusively to large observatories. Instruments orbiting Earth, perched atop Chilean deserts, or buried deep in high mountain air, carried the burden of discovery. But 3I Atlas arrived in a different era, an era when the sky is no longer the domain of a privileged few, when small telescopes, smart scopes, and sophisticated image stacking have placed astrophotography into the hands of millions. A time when amateurs driven not by grants or deadlines, but by quiet devotion have become essential voices in the unfolding narrative of the cosmos. And so, as 3I Atlas awakened in the inner solar system, humanity awakened to it. Amateur eyes on an alien traveler. It began with faint detections, small, imperfect smudges captured in backyard observatories scattered from Arizona to South Africa, from the high plains of Australia to the frozen fields of Scandinavia. At first, these images were mere curiosities, dim exposures showing a soft glow streaking quietly against a star field. But as observers refined their techniques, as they stacked dozens, then hundreds of exposures, something extraordinary began to emerge. A tail, a fange, a delicate halo of dust, a structure almost invisible in a single frame, yet unmistakable when the noise was stripped away. The early images shared on forums, astronomy groups, and cosmic photography channels became the first public record of the interstellar visitor's transformation. They appeared humble compared to NASA's deep space instruments, but their significance was far greater than resolution alone. Each new post, each careful stack, each annotated image brought the object into the realm of ordinary human experience. It became a shared artifact of wonder. And as the object brightened, the images deepened. Ordinary citizens became chroniclers of a cosmic event. The discipline of stacking. The coma of 3I Atlas, though immense, was subtle. Its jets were faint, its anti-tail nearly invisible except in long exposures. Many early observers struggled to see anything meaningful. The object appeared as nothing more than a soft speck drifting through noise. Then came the technique that unlocked the hidden world: stacking. Long exposure astrophotography gathers light slowly. Each exposure captures only a whisper of the object's form, but when hundreds of these whispers are layered, aligned, and averaged, noise fades and the signal strengthens. Structures emerge. Jets become visible. The tail stretches outward like a luminous plume. For 3I Atlas, stacking was not optional, it was essential. The object's delicate plasma features were too faint to appear in real time. Only the patient hands of amateur astrophotographers, guiding telescopes for hours beneath cold night skies, could bring them to life. Entire communities formed around this task. Observers compared stacking algorithms, noise reduction techniques, and tracking errors introduced by wind or imperfect motor gears. They shared calibration frames, dark frames, flat fields. They taught each other how to coax clarity from darkness. The result was a global, crowdsourced portrait of an interstellar object awakening under the sun's growing warmth. A web of observatories, professional and amateur. Large observatories captured the precise, high-resolution data needed for scientific modeling, but amateurs filled in the continuity. Their nightly images, taken from countless latitudes and longitudes, formed a time-lapse mosaic of 3I Atlas's evolution. Changes that would otherwise be lost became visible. A sudden brightening in the coma after a minor outburst, a shift in the anti-tail orientation as solar wind conditions changed, new jets emerging as rotational phases exposed deeper venting regions, fluctuations in brightness that hinted at internal fractures, a subtle widening of the tail preceding the CME's shock front. No single observatory could capture these changes alone, but a network of thousands could. Together, professional and amateur astronomers observed the object as a living entity, a creature shedding its icy silence and growing luminous in the presence of our star. The human element of discovery. For many observers, capturing 3I Atlas was not merely a technical achievement, it was an emotional one. They stood beneath the same sky as ancestors who gazed upward in awe. They looked through instruments they had built, repaired, modified, or saved for over years. Some imaged it from rooftops and fields, others from deserts and high mountain passes. Each saw the same traveler, the same faint glow crossing interstellar darkness. In these quiet hours, the mystery of 3I Atlas became something shared not by governments or agencies, but by people. Children pointed tiny telescopes into the night, searching for the faint glowing speck their parents had spoken of. Amateur astronomers who had spent decades photographing nebulae and galaxies found themselves drawn into something more immediate, more transient, more alive. Even individuals with small, inexpensive smart scopes captured meaningful images, proof that wonder is not limited by budget. As one observer wrote in a quiet caption beneath an image of the object's faint tail, "It's strange to photograph something older than our Sunday." Data that NASA could not produce alone. The global stream of amateur observations proved invaluable for NASA's modeling teams. While the agency prepared its high-resolution imagery, it began incorporating amateur data into trajectory models and brightness curves. The continuous imaging allowed researchers to detect short-term rotational variations, outburst timelines, coma asymmetry evolving over hours, the early signs of CME-induced disturbances, variability in jet intensity across multiple viewing angles. NASA, ESA, and independent astrophysicists soon found themselves referencing amateur data in official analyses, not as supplemental decoration, but as meaningful, scientifically relevant measurements. It marked a new era, the democratization of cosmic discovery. A planet united by a single point of light. As the live stream approached, images of 3I Atlas spread across social feeds, forums, and astronomy channels. Some were raw, some were meticulously processed, some were blurry but heartfelt. All carried the same resonance, humanity pointing its instruments large and small towards something that had crossed from another star. This interstellar object, silent and indifferent, had nonetheless given rise to a moment of collective attention, not motivated by fear, not by threat, but by wonder. And now, as the CME approached, the world's eyes, professional, amateur, and curious, turned toward the same point of darkness, waiting for the moment when a solar storm would reshape a visitor from the deep. Humanity had become the witness. The interstellar object had become the event, and in their meeting, the universe would reveal something no single telescope, no single nation, no single agency could capture alone. Even as the interstellar visitor unfurled its luminous veils, even as its jets sharpened and its coma expanded, one question remained suspended at the center of every model, every simulation, every whispered conversation among astronomers. What lies beneath the coma? What is the true form of the nucleus? It is a question that seems simple in principle. A comet's nucleus is merely a small, cold fragment of rock, ice, and dust. In the solar system, these nuclei have been photographed dozens of times, from Halley's jagged mountains to 67P's ancient lobes, from Tempel 1's battered cliffs to Hartley 2's smoky jets. Each nucleus is unique, but all follow a familiar logic of formation. Small bodies, shaped by frost and fracture, softened by eons in the deep freeze of the outer system. But 3I Atlas is not a comet of the solar system. It is not shaped by our sun's heat, our planet's gravity, or our nebular dust. Its nucleus is a relic of another star. And so, even before the CME approached, the nucleus hovered as the most elusive and consequential layer of the mystery. Why the nucleus matters? The nucleus determines everything. The intensity and pattern of outgassing, the positioning of jets, the composition of dust, the rotation state, the potential for fragmentation, the resilience or fragility under solar stress, the history encoded in its material layers. The coma is the veil, but the nucleus is the heart. If the nucleus is small, just a few kilometers across, then the massive coma and complex plasma environment become even more astonishing, requiring extreme volatile content or highly responsive dust. But if the nucleus is substantially larger, perhaps tens of kilometers in diameter, then its gravitational influence on dust and plasma must be reconsidered. Hubble's early estimate suggested a maximum size of 2.8 kilometers, but other analyses, based on coma brightness and dust production, hinted at sizes as large as 30-50 kilometers. The uncertainty was vast. The truth remained hidden in opacity, light scattered, dust saturating the view, jets obscuring the silhouettes of the solid core. And so the search for what lies beneath became a central mission for NASA's instruments. Hints from the coma's behavior. The coma is not passive. It is shaped by the nucleus beneath it. By studying the asymmetries of the coma, its brightness gradients, its uneven expansion, its density ridges, scientists can infer the underlying structure. In the case of 3I Atlas, these asymmetries offered tantalizing clues. One region of the coma appeared denser, consistently brighter across multiple observations. This brightness suggested a sustained jet emanating from a persistent vent, likely a deep fracture or hollow on the surface of the nucleus. The persistence of this feature over several rotations implied a fixed structure, not a transient outburst. Another region exhibited strange variability, intermittent pulses of dust, rising and falling as though responding to internal pressure. Some researchers believed this could indicate stratified layers within the nucleus, ice and dust in alternating bands, each responding differently to sunlight. Such layering is common in long-period comets, but the variation seen in 3I Atlas was irregular, rapid and dramatic. Cosmic ray alterations, slow, ceaseless, penetrating, may have created unstable structures within the interstellar object that fragmented or sublimated unpredictably. Possible structural types of the nucleus. As the data accumulated, several models emerged. 1. A fractured, rubble-like body. In this model, the nucleus is a cluster of bonded fragments, a loose agglomeration of ancient debris fused over time. Such a structure would produce uneven outgassing, generate irregular jets, rotate with a wobble, respond dramatically to solar heating. This model explains the tumbling rotation and erratic emissions, but it struggles to explain the stability of some jets and the coherence of certain plasma structures. 2. A compact, monolithic core. Here, the nucleus is a single, solid body with deep fractures but stable overall shape. This model matches the persistent orientation of jets, the stability of the central coma, the early awakening at distances beyond typical comet activation zones, but a monolithic nucleus of small size could not easily produce a coma hundreds of thousands of kilometers wide unless it carried an extraordinary volatile load. 3. A layered interstellar core. This more exotic model places 3I Atlas in a class shared by no known solar system object. In this scenario, cosmic rays reshape ices over millions of years. Layers of altered minerals form, pockets of volatile chemistry accumulate, internal stress create intricate vent pathways. Such a nucleus could produce the irregular jets, the pulsatile emissions, and the erratic spectral signatures observed. It would also align with plasma physicists' observations of unusual dust behavior. 4. A binary or contact binary nucleus. The nucleus might consist of two lobes, like Comet 67P. This could explain the tumbling rotation, the distinct jet orientations, the asymmetrical coma, the anti-tail alignment. But if 3I Atlas is a contact binary, its unusual dust behavior would still require additional explanations. What HiRISE revealed. Although the Mars Reconnaissance Orbiter could not directly peer through the coma, Its angular vantage provided something invaluable: coma asymmetry at high resolution. This allowed scientists to model the silhouette of the nucleus. The emerging picture suggested not a sphere, but a slightly elongated form, perhaps a cylinder or lumpy ellipsoid. The orientation of the jets supported this idea. Still, there were limits. Without a direct imaging breakthrough, the nucleus remained unresolved, a ghostly point hidden beneath a swirling mask. Possible composition. Spectroscopy hinted at materials familiar yet unpredictable. Water, ice, carbon dioxide, carbon monoxide, hydrocarbons, possibly ammonia. But interstellar exposure likely introduced exotic ices, crystalline structures altered by cosmic rays, carbon-rich dust with unusual charge behavior, porous materials capable of sudden outbursts. One hypothesis proposed that 3I Atlas might include supervolatile pockets, materials that sublimate at much lower temperatures than water ice, such as nitrogen or neon compounds. These could explain the early activation far from the Sunday. The nucleus as an interstellar record. Whatever its final shape and composition, the nucleus of 3I Atlas carries the imprint of its origin, whether from a young planetary system, a shattered moon, or the debris field of a disrupted exoplanet. The coma is its language, the jets are its pulse, the plasma is its interaction with our star. But the nucleus, the cold, ancient heart, holds the memory of another world. Awaiting the CME's revelation, scientists knew that the CME, when it arrived, might reveal what the coma had hidden. Compressing plasma boundaries, clearing dust along magnetic gradients, altering the coma's opacity, briefly exposing views closer to the nucleus, triggering outbursts that reveal structural weaknesses, shifting jet orientations to trace deeper fractures. In this sense, the coming storm was not merely an external influence, it was a probe, a natural instrument that might illuminate the hidden core. The world awaited NASA's revelations. NASA awaited the CME. And the CME approached an object whose nucleus had been shaped by stars long vanished. What lies beneath the coma is not merely a geological puzzle, it is a relic of a different cosmic neighborhood, a witness to a chemical and physical history older than the Earth itself. The great storm from the Sun was still surging outward when the final theories began to settle into place, partial, tentative, woven with uncertainties, yet weighted with a sense that the universe was offering more than raw data. It was offering reflection, context, a reminder of the fragile place humanity occupies in the vast and shifting architecture of the cosmos. For as the CME approached, as 3I Atlas brightened into full awakening, the event came to resemble something deeper than a scientific encounter. It felt like a cosmic parable, a wanderer from another star passing close to our own, illuminated and altered by the breath of the Sunday, a meeting not of objects, but of histories, ours young and bright, its ancient and cold. And in this meeting, questions emerged that no image or spectrum could answer. What does it mean for a star to touch an interstellar body? The Sun has never seen 3I Atlas before. For millennia, for eons perhaps, the traveler drifted in silence, untouched by any star's warmth. Now, for one brief pass, it experienced the full force of a stellar environment: light, heat, radiation, wind, and storm. Such encounters are rare. The galaxy is vast. Stars sit scattered like solitary fires across billions of miles. Most interstellar objects wander alone forever, illuminated only by the faint glow of distant starlight. For 3I Atlas, the Sun became not just a light source, but a sculptor heating it, shaping it, awakening it from cosmic dormancy. The CME, too, is more than a solar eruption. It is a message of the sun's vitality, a reminder that stars are not static, but living furnaces whose moods ripple across the worlds that orbit them. When such a storm meets an object from elsewhere, the boundaries between systems blur. The sun becomes an actor in a story that began in another stellar nursery. In that moment, humanity witnesses not a collision, but a conversation, star to wanderer, heat to ice, plasma to dust. A bridge between two cosmic histories. Every atom in 3I Atlas carries memory of the star system where it formed, the radiation that shaped it, the gravitational tides that cast it loose. In touching our own star's winds, however briefly, it becomes part of our solar system's story too. This meeting is symbolic, a bridge between worlds that never knew each other. For humanity, whose entire recorded existence spans only a sliver of cosmic time, such encounters deepen the understanding that our solar system is not isolated. It is permeable, connected. Material flows between stars. Dust and ice drift across the galactic medium. Comets formed around distant suns occasionally pass through our skies. The boundaries of home are not fixed. They are porous, softened by the slow currents of galactic motion. What the object teaches beyond science. 3I Atlas, for all its jets and plasma channels, for all its mystery, carries one truth that scientists and philosophers alike have long recognized. The universe is dynamic, alive with motion, interaction, and change. Its presence teaches that the galaxy is filled with countless wandering fragments, that the chemistry of other star systems flows eventually into ours, that the sun's influence extends far beyond the planets, that cosmic isolation is an illusion, that even in the coldest regions between stars, objects retain the potential for transformation, and in the quiet heart of these lessons lies something more profound, a reminder that the human species is still young in its cosmic perspective. Each new interstellar visitor widens the window through which we glimpse the broader universe, the fragility of knowledge and the vastness of the unknown. As the CME approached, scientists were humbled by an uncomfortable truth. For all our telescopes, our models, our laboratories, there remains far more unknown than known. 3I Atlas exposed this humility. Its jets defied simple thermal models. Its plasma environment resisted standard cometary physics. Its dust behaved as though born of different principles. Its nucleus remained unseen, inferred, elusive. Its interaction with solar forces remained unpredictable. In every attempt to categorize it, the universe whispered the same reminder. Certainty is temporary. Mystery is eternal. This realization is not a setback. It is a gift, a widening of imagination, a deepening of inquiry, a humbling of perspective. Humanity in the shadow of the infinite. To watch a traveler from another star drift through the solar system is to confront one's own scale. The Earth becomes small, beautiful, but small. Its boundaries appear fragile. Its histories appear brief. Its civilizations appear transient, like dust grains in a vast, swirling coma. The interstellar visitor does not notice us. It does not alter its course. It does not offer explanation. It simply moves touched by sunlight, shaped by plasma, illuminated by human curiosity. Yet its silence carries meaning. It tells us that the universe is older than we comprehend. Stars live and die, flinging debris into the dark. Planets form and fragment. Systems evolve and dissolve. The galaxy is a sea of wandering matter. And in that sea, for one moment in time, our star and a distant traveler meet. A reminder of our place. As NASA prepared its imagery, As telescopes across Earth continued to track the visitor, as the CME closed its final kilometers, a deeper understanding settled across the scientific community and beyond. We are part of a universe in motion. We are witnesses to processes that shaped the Milky Way long before Earth existed. We are observers not outside the cosmos, but within it. 3i Atlas, in its beauty and strangeness, reminded humanity that the universe is far larger, far older, and far more intricate than our current models allow. It invited reflection not on fear nor on threat, but on connectedness, curiosity, and the endless reach of discovery. The emotional close, the long exhale. And so, as the interstellar wanderer approached the moment when the sun would touch it with a storm of fire, the world paused not in dread, but in wonder. Here drifted a relic from another star. Here approached a CME from our own. Here, in the quiet vastness between planets, two cosmic histories converged. It is a simple encounter, a natural one, but in its simplicity lies something almost sacred. A reminder that our universe is alive, with moments of silent, magnificent connection, moments we are privileged to witness. And as the traveler continued its journey, glowing in the solar wind, humanity looked upward and felt, if only for a moment, the profound humility of existing within a cosmic story still unfolding. The storm will pass, as all storms do. The interstellar traveler will continue on its long, indifferent arc through the solar system, reshaped but not halted, awakened but not undone. And in the stillness that follows the CME's fading breath, its dust will settle into new patterns, its coma will soften, and its jets will find quiet rhythms once more. For a brief time, it will remain visible, glowing faintly against the cold backdrop of space before receding into the darkness from which it came. In this gentle aftermath, the pace of the story slows, the urgency fades, the flashes of magnetic turbulence give way to a soft, steady glow. What was once dramatic becomes contemplative. The object drifts in its familiar silence again, and the universe resumes its quiet, unbroken hum. It is here, in this calm, that the meaning of the encounter settles over us like starlight. We begin to understand that not every cosmic moment is defined by violence or spectacle. Many are defined by tenderness, by the subtle shaping of dust, by the faint whisper of plasma, by the soft illumination of sunlight on an ancient surface. The universe speaks most clearly not in catastrophe, but in the gentle unfolding of its natural rhythms. And as we watch the interstellar visitor fade into distance, we are left with a feeling not of loss, but of gratitude. Gratitude for the chance to witness this meeting of star and wanderer. Gratitude for the reminder that even in an immense universe, small moments can hold infinite meaning. Gratitude for the quiet reassurance that our curiosity, our desire to know, to understand, to look upward, connects us to something larger than ourselves. The traveler moves on. The storm dissolves. The night grows soft once more. And in that softness, we rest. We breathe. We dream. Sweet dreams.